All right, good afternoon, everyone. Let's get started with lecture 20 about the second lecture of distributed training. So in the last lecture, we talked about several parallelization techniques. So today we are going to continue to discuss how to combine these techniques using mixed parallelism, hybrid parallelism, 2D and 3D parallelism, and also how to auto-parallelize the training. And also understand the bandwidth and communication latency bottleneck of distributed training. And to overcome the bandwidth bottleneck, we're going to talk about gradient compression, how to compress the gradients to overcome the bandwidth bottleneck, including the gradient pruning using sparsity and like deep gradient compression, where we can compress the gradient by 100 times without losing accuracy. And also how to perform gradient quantization, 1-bit SGD and ternary gradient. And finally, to overcome the latency bottleneck, we are going to talk about delayed gradient update to overcome the latency bottleneck. So let's first start with hybrid and mixed parallelism, and also how to auto-parallelize. As a review, for the last lecture, we talked about 4 strategies for parallelization for distributed training. The first one is data parallelism. Okay, so separate pieces of data. The data is splitted across multiple nodes. We have n copies of model. Each GPU is maintaining its own copy. That has pretty good utilization, memory cost, but it's high memory cost and low communication. And there's some optimizations on top of the data parallelism. Instead of each GPU has the entire weight, entire gradient, entire optimizer state, we talk about 0, 1, 2, 3 FSDP techniques to shard the optimizer state, to shard the gradient, and also shard the weight. So you don't have to store the entire copy of the weight within one GPU. Second technique is the pipeline parallelism. So this is one kind of model parallelism because you are splitting the layers of the model. Okay? And with a single copy of the model, that has low utilization because if different pipeline stage, the latency is different. The slower one, the fast one has to wait for the slow one. Low memory cost, medium communication. You only need to communicate between the pipeline stages. So the next one is tensor parallelism. So it's another model parallelism approach, but you are splitting the model within a tensor. I have a single copy of a model. It has high utilization, low memory cost, but high communication. Like in transformers, how many communication, which stage do we need communication? So for the attention, you need one communication in the beginning and the end. For the FFN, the 2 FFN layer, you need one communication in the beginning and the end. So high communication cost. Lastly, we talk about the sequence parallel, where we are handling long contexts, long documents, long videos. When there is a lot of tokens, we want to split the token across multiple GPUs. So we can split the data by the tokens. The first GPU deal with the first chapter, the second GPU deal with the second chapter. But there is actual communication during the attention layer, since different parts of the document still need to attend to each other. And therefore, we talk about 2 techniques. One is the Ulysses technique. You want to do all reduce for each GPU to get the attention from each document for a different part of the document to each other. We also talk about the ring attention, where we can perform this ring all reduce to communicate between different GPUs. Okay? So that's the 4 parallelization methods. The next question we want to answer is, can we combine the merits of different parallelization methods and perform 2D or 3D, a combination of different techniques? So let's talk about 2D parallelism. This is one possible example. You can see at the outer loop, we are using data parallelism. So this is one group, this is one group, so rank 1 and rank 0. On the outer loop, we are using data parallelism, feeding different parts of the data to rank 1 and rank 0. And in the inner loop, we are using pipeline parallelism. So this is forward 1, forward 0, backward 0, forward 1, backward 1. So we are alternating between two GPUs to do pipeline parallelism. Okay, so this is 4 GPUs, 2 by 2, with 2 hierarchies. Okay, one is doing the data parallelism in the outer side, the other 2 is doing pipeline parallelism in the inner side. Of course, we can do other arrangements. For example, here we are performing pipeline parallelism in the outer loop. So this is layer 1, this is layer 2, and we are doing the partition such that these 2 layers are performing pipeline parallelism. In the inner loop, we are doing tensor parallelism. So this is the first half of the tensor, this is the second half of the tensor on the top and on the bottom, respectively. So one matrix is divided into 2 sub-matrices. Okay, so this is tensor parallelism in the inner loop and pipeline parallelism in the outer loop. Let's see another hybrid parallelism by combining different sequence parallelizations. Okay, so this is a conventional approach, just to use the auto ring attention approach. Okay, so everywhere is using ring attention. So here, assuming every GPU within this dashed rectangle is within a node. So this is one node. This is the second node. We have 2 nodes. Between the node, the communication bandwidth is about 50 gigabytes per second. But within the node, the bandwidth could be much higher, could be as high as 900 gigabytes per second. Okay, so using this 1D sequence parallelism using ring attention will underutilize because we have to stick to the slowest, which is the inter-node communication bandwidth, and we are not well exploiting this high bandwidth for NVLink within the node. So how to better exploit the high bandwidth provided by NVLink? We can perform such 2D attention. So within the node, we can perform all-to-all communication using the Ulysses approach. And between the nodes, we can use this ring approach, ring attention, which has lower bandwidth. Okay, so we are using ring attention between the nodes and all-to-all repartition within the node. Okay, so this is the all-to-all repartition we talked about in the last lecture. So in this way, we can fully exploit the high bandwidth within the node and lower bandwidth between the nodes. So this is 2D sequence parallelism. We can also have 3D parallelism. So combining this pipeline parallelism with tensor parallelism with data parallelism. So this is 3D parallelism. Okay, so the same color of the GPUs are on the same server. You can see within the server, we are doing model parallelism. Since model parallelism is it's also called tensor parallelism. It's most communication heavy, so we put them in the same server. And then we are doing 0 data parallelism in this dimension, and we are doing pipeline parallelism by splitting the layer in the vertical dimension. So that's the 3D parallelism. So that's a pretty large design space. So the next question is, how do we auto-parallelize? So when the model is too large to fit the GPU, we can either split the model using pipeline parallelism to split different layers. But even if a layer is too large, we can split the layer by using tensor parallelism. Okay, so this is pipeline parallelism, GPU 1, GPU 2, layer 1, layer 2. This is tensor parallelism. Either within the GPU, within a single GPU, within a single layer, we can divide the tensor by 2 in this case. But how do we find the best parallel strategies? For each layer, there's already a lot of choices. If you have so many layers, what's the best choice? So here I introduce ALPA, which is a unified compiler for distributed training. So given a computational graph, 4 layers in this case, this is a pretty large search space between the layers and also within the layers. We can either partitioning them by 2 plus 2 or 1 plus 3 or 3 plus 1, even within the each group, we can either partition the tensor vertically or horizontally. So alpha proposes hierarchical search space. First is inter-operator parallelism. Okay? So layer 1 is a group, layer BCD is another group, or layer AB is a group, CND is another group. Second hierarchy is the intra-operator parallelism. Okay? So we can partition B, C either horizontally, vertically, horizontally, or vertically, horizontally, horizontally. Okay, so breaking them into these two hierarchies. And then alpha will search for the inter-operator parallelism. So given a computational graph, stage 1 can either include these two layers or this one layer. Stage 2 either a single pooling layer or this conv average pool like mod. Okay, so different approaches. You can use dynamic programming to divide the stages, either it's 2 plus 1 plus 2 plus 1, or 1 plus 3 plus 1 plus 2. Okay. The next, alpha can search for the intra-operator parallelism. Okay, so given this A times B, we get a matrix multiplication to get a C. Okay, we can either replicate the B and split the A across the two GPUs, or we can replicate A and split B across the GPUs, or we can split both A and B to get a partial sum, and finally do all reduce to sum them up. So this is different design choices for the intra-OP parallelism. And then we can calculate the cost function, which is compute cost plus communication cost plus the resharding cost between the operators. So given a computational graph, given a device cluster, it will first do the inter-operator pass and then intra-operator pass to do the cost estimation, and then give you the best orchestration after this automatic search. And actually, that can actually match almost perfectly with the best manual design system across 1, 4, 8, all the way to 64 GPUs. Okay, and this is comparing the best manual system versus alpha. Alpha can achieve a much higher throughput compared with the best manual system. All right, so that is a hybrid, mixed parallelism and auto-parallelize. And now let's try to understand the bandwidth and latency bottleneck of distributed training. So as the fundamental, computation is cheap, data movement is expensive. So communication is very essential. Okay? Communication is the foundation for distributed training. There are several issues when the model gets larger. Okay, so first we require synchronization. So synchronized SGD is still much more widely used in the industry these days compared with asynchronous SGD. But synchronization will lead to high communication frequency. We always need to synchronize after each iteration. And the models are getting larger these days, which means we need to transfer a larger gradient, because the dimension of the gradient is equal to the dimension of the weight. If the model weight is larger, the gradient that needs to be transferred is also larger. And also, when you have more training nodes, if you want to make your training faster, like from an hour to a few minutes, you need to introduce more training nodes, which means more communication between the nodes using like all reduce, lead to longer latency. Okay, so if you have more node, the communication time actually will be larger compared with the computation. So on the right-hand side, it's showing this is the ideal speed up. If you have 200 GPUs, ideally you want to have 200 times speed up. But different models have different scalability. Like AlexNet has very poor scalability, or Inception model has much better scalability. And that is because AlexNet, you have a lot of weight, 240 megabyte, 60 million parameters. So, but relatively low compute flops. You do a little computation and you have to do a lot of communication. That's why such model is having much worse scalability. 200 nodes, 200 nodes, 200 GPUs, you have only 100 speed up compared with 200. And finally, the networking bandwidth, if it becomes a bottleneck, it will slow down the distributed training. No matter how fast your computation is, how strong your computation infra is, if the bandwidth of your network is low, you still cannot fully unleash the power of the powerful newer generation of GPUs. So let's see, what is the scale? How do we estimate the networking latency? So let's go through different scenarios. So within a rack of server is roughly millisecond or microsecond level. Okay, so as you go through within the data center is millisecond level latency. As you go to wireless communication, that's roughly 100 millisecond networking latency. But if you want to send a message across the world, it's 100 millisecond or second level latency. So the smaller the latency, the faster the training speed. Well, if the latency is too long, the training speed will be much lower. So let's talk about techniques to overcome this networking bandwidth bottleneck by introducing two chapters. One is the gradient pruning, the other is gradient quantization. Okay, so let's first start with how do we reduce the transfer data size. Let's recall this workflow of parameter server-based distributed training. So we have a parameter server that holds this neural network model. The first step, each worker will pool the parameters, get a local replica of the neural network model. It's going to get a split of the training data, a data parallelism. So it's going to calculate the local gradient given the training data and the model. After it completes, it will push the gradients to the parameter server. And the parameter server will synchronize across multiple workers and finally update the server. So this step, pulling the parameters and pushing the gradient, okay, actually this will be the bottleneck of the networking bandwidth. Imagine you have 100 nodes, they each has to push the gradient to the parameter server. Or even if you do ring or reduce, you still have to communicate a lot of gradient, which is of the same size as the weight. So natural idea is, can we prune the gradient? So this is the original gradient tensor. Can we prune them by setting a lot of them to be 0, such that we don't need to send those pruned 0 gradients? Okay, we only need to send these dark green gradients and make these light green area blocks. We don't send them. Another approach is, rather than sending this 32-bit gradient, can we quantize the gradient to 8-bit and send a much lower precision gradient? So this is 8 times saving compared with sending everything else, everything in 32-bit. So that's roughly 2 directions we can do to reduce the transfer data size. Let's visit them one by one, and let's first visit the pruning and sparse communication approach. So let's discuss gradient pruning with local gradient accumulation. Okay. So the idea is to only send the top k gradients ranked by the magnitude. So this is the gradient tensor, and we find the top k by sorting them. And these green blocks are the top k gradients. Of course, there will be a error, right? and we can accumulate the error. For example, for the pruned area, like everything here pruned at 0, they must have a residual. Okay? They are small, but they do have a residual corresponding to the 0 gradient. Rather than sending away those residuals to the parameter server, we want to accumulate those gradients locally. Okay? Hopefully next time the gradient will get bigger, past the threshold, and we'll send them out. And before they accumulate to pass the threshold, we just keep the residual locally without sending them out. So that can indeed improve the training speed. This very early paper, like 7 years ago, was showing on a NIST data set can increase training images per second. But it fails on slightly larger network, like ResNet. There is 1% loss of accuracy, which is not tolerable. So how do we solve the issue of loss of accuracy when we are pruning the gradients? And figure out where is the performance degradation coming from? Why the performance accuracy dropped? Actually, that is due to the momentum. So let's review what is the momentum. So momentum is a very important technique used in the gradient descent. Nearly almost all the optimizers has momentum these days. It's very useful to overcome the local minima and oscillation. It's very widely used, AlexNet, VGG, ResNet, Transformer, BERT, even these days for large language models. Momentum is very widely used. Here we consider only the first order momentum. Okay, so this is the gradient in blue, and we update the velocity in U, and M is the momentum. It's a discounting factor. We take a percentage of the previous velocity and we add the current gradient, we get the current velocity. And we use velocity rather than a gradient to update the weight. Okay, so this is a discounted velocity, this is the current gradient, this is the new velocity, which is a combination of the previous velocity and the current gradient. And we use that to update the weight. So during the SGD, we first obtain the gradient. Okay? The gradient is in blue, and then we calculate the velocity using the momentum. Okay? So this is the previous velocity, ut minus 1, and this is the ut by combining these two together to calculate the velocity ut, and we update the model weights by ut, not by gt. Okay? Not using gradient, but using momentum. About using velocity, and using this ut to update the model weights. And finally, we repeat and calculate the velocity for the next iteration. Okay, so this is the new gradient, and this is the discounted factor of the previous u is the velocity. Okay, so this is ut this long. This is a shorter version of that because it is a scaled version of that. Okay, so this is ut plus 1. And we use ut plus 1 to update the weight. We are not using gt plus 1 to update the weight. So that's the key point here. And let's see, during sparse communication, what is accumulated? We are accumulating the gradient. Okay, so the residual gradient is accumulated in the local buffers. Before they get large, they don't get sent out. They only get sent out after they get larger. So in the previous algorithm, we directly use the accumulated gradient for momentum calculation. So we are accumulating a gradient. Is that correct? Like here, if the gradient is not sent out, we accumulate them locally. Hopefully, during the next iteration, it will get larger and get sent out. So let's see how that looks on this graph. So this is the vanilla momentum SGD. We get ut, we get ut plus 1, we get 2 updates, and the weight started from here, get here, finally it landed here. And the momentum SGD with local accumulation, we are accumulating the gradients in the local buffer. If the gradient is small, we accumulate them. After they get large, we send them out. So this is the accumulated gradient. What if we use that to update the model? It will become here rather than here, right? So you see the difference. Here we are accumulating the gradient and I get a wrong update using momentum SGD with this naive local accumulation. So it's wrong to add the accumulated gradient, resulted in the optimization shifted, doesn't match. Okay? So what should we do? We should accumulate the velocity, not the gradient. So what is the velocity? So this is ut, this is ut plus 1. We should accumulate the velocity by combining ut and ut plus 1. We get the red accumulated velocity. And we use that to update the model weight. Okay, so we should accumulate the velocity over many iterations rather than accumulating the gradient. And in this way, it can land into the same position in these two scenarios. So here's a comparison among the vanilla momentum SGD without momentum correction with momentum correction. Okay, so the next technique is warm up the training. So in the early stage of the training, the network weight is changing very rapidly. And local gradient accumulation, stale gradient, will make the problem worse. So we don't want to have a very high pruning ratio in the first couple of iterations. So when the optimization just getting started, the gradient may be pretty large. So we can warm up the learning rate. Initially, start with a very small learning rate and gradually here is linearly increasing to the stable learning rate. Since you can see on the initial training stage, the gradient is very sharp, so we want to be conservative to prevent overshooting by using a smaller learning rate. We can also warm up the sparsity to avoid the sudden change in the sparsity. So here, we are gradually increasing the sparsity. Here it is exponentially increasing the sparsity in the first couple of epochs. Here are 4 epochs to help the optimizer adapt to a larger sparsity. In epoch 5, it becomes stable. Sparsity becomes stable. So let's see how this technique improves the accuracy by starting with the local gradient accumulation. The baseline model has accuracy of 92%, 92.9%. If you just do naive gradient pruning without doing any gradient accumulation, it doesn't converge, so you cannot do that. If we add local gradient accumulation, if the gradient is small, we accumulate them until they get large and send them out. It can recover a lot, but still is 1.56% lower than the baseline. What if we add this local gradient accumulation plus this momentum correction? Okay, so accumulate the velocity rather than accumulate the gradient. It becomes 92.56, a lot better than the baseline. What if we only add the warm up? It's also get better, from 91.3 to 91.8. What if we add them together, including local gradient accumulation, momentum correction, and warm-up training? Combining them all, it further increased to more than 93%. And now it's getting even better compared with the baseline. So this is vision, and this is language modeling. Okay, so the word error rate is also well recovered by combining all these techniques. The lower the better on the right hand side. If we just do this local gradient accumulation, actually there is 3-point degradation for the word error rate. If we add the momentum correction to accumulate the velocity rather than accumulate the gradient, and also do local gradient clipping, which is quite important for LSTM, which we want to prevent the gradient vanishing and gradient explosion problem. So we want to also do this local gradient clipping. It can recover a little bit, around 1%. And then we can add a momentum correction and local gradient clipping. It further improved a little bit. And finally, if we combine all the techniques, it can be further improved to 10.37. Okay. So let's see the training curve. What does the training curve look like? So this is the accuracy on the left. The higher the better. This is the loss on the right. The lower the better. And if you can see here, the baseline is in blue. And there are several approaches. One is doing gradient dropping in red. Actually, it's much worse. It's on the bottom, so the accuracy is not good. And the loss is the highest, so the loss is not good if we just perform gradient dropping. The yellow one is gradient sparsification with momentum compression. Only sparsification with correction without warm up. It is in yellow right here. It's better, but it's still worse compared with the baseline. It's yellow here. And deep gradient compression is in purple. Purple is closely matched with the baseline. And here is in purple. It's even lower than the baseline. So this is on Sapphire 10. Surprisingly, we can make it 99.9% sparse for the gradient. ImageNet is about 200 to 500 times gradient compression ratio. It's also quite significant. DGC stands for deep gradient compression. This is the top 1, top 5 accuracy. Gradient size is reduced by almost 600 times. Why it's not 1,000 times? Because it's almost 99.9% sparsity. Why the gradient size is reduced by like 500 times? Because there's indexing overhead, of course, to represent a sparse array. You need indexing overhead, and also the biases are not pruned. Remember, in the light residual training, we want to keep the bias. Bias is very important. So this is the VGG trained on ImageNet, top 1, top 5 accuracy, the baseline versus deep gradient compression. Compression ratio is more than 200 times. So not only on vision, let's also take a look at the language modeling. So this is comparing the baseline deep gradient compression for the loss, and this is for the perplexity. The perplexity is very well maintained, but the size of the gradient reduced from 190 megabytes to only less than half a megabyte. And this is for speech recognition. The word error rate is also well maintained versus the loss. Previously, the gradient is 480 megabytes, now it's less than 1 megabyte. Okay, so what is the problem for deep gradient compression if we have using the all-reduce approach? Actually, after a few iterations, it will get denser. Right? So you suppose we have 4 nodes, 0, 1, 2, 3. And the sparsity of each node of the gradients are all different. For node 0, these bottom 3 gradients are 1. On node 3, the other 2 values are non-zero. If you want to perform this all-reduce operation, okay, reducing this and this, so adding 3 to 0, it will get denser. And if you do another iteration, it will continue to get denser. So it will get denser and denser. If you repeat this all-reduce process, send 3 to 1 to 0, 0 to 1, 1 to 2, 2 to 3. Okay, you can imagine the final accumulated result will get denser. So what's the solution here? So we can enforce the same sparsity pattern, so when we do all-reduce, it will not get denser. And you can apply the coarse-grained sparsity, okay, coarse-grained sparsity, such that you can enforce certain pattern of sparsity. And also you can continue to prune in the middle of this ring or reduce. For example, prune in the middle of the ring or reduce. Prune away some of the non-zeros to be zero again. Okay. There's another approach rather than using sparsity. Remember during the inference efficiency technique, we talk about a lot of techniques. One is low rank, right? So we can not only use sparsity, okay, by pruning a lot of small gradients, we can also factor the gradients using low rank. So this is using a rank of 1, factoring this 4x4 matrix into a 1x4 times 4x1 matrix. Okay, so the advantage is that the low rank matrix dimension, 4x1, 1x4, that's the same across all the servers. So when you are doing a ring or reduce, you are not going to get any difference. Not like the sparsity, you can get denser here, and will not get denser or sparser. The dimension is the same as you perform or reduce. And let's see how that performs. The speed is actually doing quite well. This is rank 2. The speed up over the standard SGG is much better. Almost a linear speed up when the number of workers increase when using this power SGD approach. Okay, so this is the comparison of different gradient pruning methods. Okay, we can perform sparsification. Start with local gradient accumulation. Okay, if the gradient is small, then we can accumulate them until it's large. After it exceeds a certain threshold, we send them out. Unfortunately, it can have a low sparsity ratio, otherwise the accuracy will drop. And then we introduced the deep gradient compression technique, which we published in 2017, by using momentum correction, which we discovered we should not accumulate the gradient, but we should accumulate the velocity, not the gradient. So we call it momentum correction, which can solve the issue of low sparsity ratio issue. And gradient clipping, okay, so we want to clip the gradient to prevent overflow, and also perform warm-up training. Start with a smaller learning rate, start with a smaller sparsity ratio to warm up. That can achieve very high sparsity ratio. We can prune away 99.9%. So for weight pruning, even 90% pruning is a very high pruning ratio, but gradient is much easier to prune compared with the weight. So that's the lesson we learned while maintaining the accuracy. However, this sparsification technique have a limitation where it will get denser if you do this ring or reduce for a few iterations. Therefore, we talk about this power SGD using the low rank approach, okay, instead of fine-grained pruning, to make sure during the communication it will not get denser. Okay, so that's the first half of this lecture. Let's take a 5-minute break before we jump into quantization approach. All right, welcome back. Let's continue the discussion about gradient quantization. Just now we talked about the first technique of gradient compression, which is pruning, to remove a lot of gradient. Now let's see, can we use 1 bit or ternary 2 bits or only 3 numbers to represent the gradient? So this is 1 bit SGD. Okay, so starting with the 32-bit full precision gradient tensor, we want to quantize them to only 1 bit plus a delta, which is the residual, which we can accumulate locally to accumulate the quantization error. So in the next round, we can add this residual to the next iteration, and hopefully we can alleviate the error coming from this aggressive 1-bit quantization. And of course, we can apply column-wise scaling factor. So we can have a scaling factor for each column rather than just 0 and 1. We can apply a scaling factor, FP32 scaling factor for each column. So the whole solution will be like this. We have the original gradient, and we set a threshold to be 0. If it is greater than 0, we set it to 1, otherwise it's 0. Okay? And across each column, we calculate we find a scaling factor by maintaining the sum to be the same, the absolute value sum to be the same, such that we get the quantized value, okay, and we can calculate the gradient residual, okay, what is the quantization error. Different from inference, where this error is indeed an error, it will propagate. For training, we can accumulate the error, okay, add it back. Since they're both at P32, we can add it back to the original gradient to get the updated gradient. Okay, so the next iteration, we can continue this flow. Another approach is to set a threshold. Rather than set a 0 threshold, we can set a threshold tau. Okay, it's also a reconstruction value, which is chosen in advance. So if it is greater than tau, the value will be tau. In the middle, between tau and minus tau, it will be 0. If it is smaller than minus tau, it will be quantized to minus tau. So the drawback here is to empirically choose the value tau. Okay? Similarly, it also has the mechanism of gradient quantization error accumulation. So this is threshold quantization. The next work is called ternary gradient, okay, which is saying, can we quantize the gradient divided by the max of the gradient to be 0, 1, and minus 1. But it's probabilistic quantization. So with probability, the magnitude divided by the max value. Okay? So usually adding such stochastic quantization will improve the accuracy, and that's indeed the case. Okay? So the expectation of the quantized gradient will be the same as the original one. So there is no quantization error accumulation, since the expectation is matching in this way, that's guaranteed. So we don't need to accumulate the error. So we can do iteration by iteration. It's independent. It's done on the fly. Okay. So this is the ternary grad. All right. So that is the two solutions for gradient compression to overcome the communication bandwidth bottleneck. And the other bottleneck beyond the communication bandwidth is actually the communication latency. Okay, communication latency. And we are going to talk about techniques to solve the latency bottleneck by using delayed gradient update. And first, let's review the concepts between quantization, between bandwidth and latency. Okay, so bandwidth is much easier to improve compared with latency. For example, we can improve the bandwidth by compressing the gradient, make it smaller, and quantize that, make it a fewer number precision. For example, using the technique we just learned, using pruning, deep gradient compression, TernGrad gradient quantization approach. We can also upgrade the hardware. Okay, so Ethernet has 100 megabits to 1 gigabit per second. This fiber has about 1 gigabit to 25 gigabit per second. We can also upgrade it to the InfiniBand, which can easily get 400 gigabit per second these days. So the bandwidth can be improved by upgrading your hardware. However, latency improvement is very hard. It's restricted by physics. You have physical limit by the speed of light. For example, traveling from Boston to Shanghai at the speed of light still takes 162 milliseconds. Okay, so that's the physical limit. There's also possible of the signal congestion, like in urban offices and homes, creates a lot of signal contention. So latency optimization is very hard. What's the bottleneck? Why do we want a low latency during distributed training? So for example, we have two workers. The green part is the computation. The yellow part is the communication. And we have to synchronize after each iteration. So we have to wait for the communication to finish before we can start the second iteration of computation. Okay? If the latency increases, the yellow part, which is communication time, will increase. And worker 1 and worker 2, they cannot start the next round of computation before the communication finishes, since they need to synchronize. Okay? So that will increase the total latency. So the workers have to wait for the transmission to finish before the next step, since the local updates and communication are happening sequentially. So this is too bad. If we have a longer networking latency, the total training will get much slower. And the question here is, can we find an alternative solution? So to allow the stale gradients, okay, allow the gradient to be stale. We don't have to be blocked, but we want to continue to make progress. So we can overlap communication with computation. Okay, so this is similar to using the late days to submit your homework. Okay? To transmit your gradient, to use the late days. Right? When we are submitting the homework, like homework 2, we can make progress by continue studying about lecture 3 before we finish homework 2. Right? We can submit the homework 2 while still making progress by learning lecture 3. Okay? And we can submit. We no longer has to be blocked by using the late days. So let's see what does that look like by using such delayed gradient averaging. Okay. So let's see. These are 4 iterations with using distributed SGD. There's a long delay to send and receive those parameters of the gradient. Okay. So we cannot start step 2 computation before we finish this communication. They are blocked by this long synchronization. But if you allow such delay, we can immediately start the second iteration after the first iteration completes, even though we haven't finished the send and receive about the gradient. We can continue to make progress. Computing step 2, step 3, step 4, and suddenly we received the gradient coming from step 1, which is a stale gradient with respect to step 4. Okay, it was 3 steps before, so that's a stale gradient. But fortunately, our study in this paper find it's still possible to converge perfectly by using stale gradient to a certain extent. At least 3 steps is very safe. Okay, so this is called delayed gradient averaging. We are summing up the gradient coming from a previous step. It's delayed, but it can still converge. So step 4 receive the gradient from step 1. It's going to make progress, and step 5 is going to receive the gradient from step 2. So we are not losing anything. We are just using the stale gradient. We are not skipping any gradient. So all the gradient are transmitted. All the homework is submitted, even though we are using the late days, right? So there must be a certain threshold, like our lecture, we have a fixed number of late days. Beyond that, we don't allow, and beyond that, the model will not converge. So that's the same principle. Let's see what happens if we increase the communication latency in this way. So previously, we have to synchronize after each iteration. Have this barrier. Okay, the red one is the synchronization barrier. If we allow 1 iteration of delay, we can remove this barrier in the first iteration, as long as on the second iteration we can synchronize. Okay, so this is 1 day of late day of a homework. So this is the communication. So the communication, if it gets longer, as long as it doesn't exceed this barrier, it will not increase the total latency for the training, okay, as long as the communication finishes before this barrier. So the total training time is not affected, even if the latency increased. Okay? So the key idea is to delay the receiving timing of the ith gradient to a later iteration, I plus d. And we are receiving a stale gradient d steps away. So let's see how that works. So we initialize a container for each iteration's gradient called G, And for each training iteration, we calculate the gradient using the network weights and the data. We calculate the local gradient G, and we send our local gradient out, send it out to other nodes with the iteration as the ID. And then we record this G in this array, saying that for this iteration, the gradient is G. And average G is received D steps ago. Okay, we receive from ID equal to iteration minus D. So that's delayed by D steps, which we finally received, since the receive function takes time. When we received it, it's already D steps away. And then when we are doing the update, the weight equal to weight minus the learning rate times the G is our freshly calculated local gradient, and we want to subtract the gradient from the current node that was D steps away. Since we have already received the averaged gradient from all the servers D steps away, we want to compensate that by subtracting the current node's iter minus D steps away is gradient. That's why we need this G vector to record the gradient of each step, of each iteration. And finally, we receive the average gradient from other node. This average G is actually delayed by D steps. So that's the only change we need to make. Okay, subtract the gradient from the current node as D steps away, since we are compensated by receiving the averaged gradient from all the nodes. Let's continue to deal with the staleness. So we have seen this figure already. Let's compare without the correction. If we directly apply this weight equal to weight minus learning rate times the stale gradient that is averaged across all the nodes, what will happen? Actually, the longer the delay, actually the accuracy will drop very quickly from 88% to 84 to 84%. Okay, this is a delay. As you get longer delay without any correction, the accuracy will drop. So let's see, how do we apply the correction term? So we should subtract the gradient coming from the local gradient that is D steps away, and add the current, the fresh gradient from the current node, and add the delayed gradient that is averaged across all the nodes but D steps away. Okay? Since this already contained part of the local gradient that's D steps away, so that's why we should subtract it. That's why we should subtract it, since this term already contained this term. And after applying such correction term, we can well maintain the accuracy much better than without correction, up to like 4%, 5% better compared with without using this correction term. So the take home is that we can allow such staleness by using the gradient, average the gradient D iterations away, but don't forget to subtract your local gradient, otherwise we will duplicate both from your own gradient, since it's already added here, and also from the sum of the stale gradients. Question?
Doesn't the learning rate have to stay constant?
So within these steps, we assume the learning rate stays roughly the same. D is not too large, it's only like 10, 20 iterations.
Compared to standard gradient descent, I assume you have to use smaller learning rates to make sure that these adjustments with the delay don't lead you to big overshoots or undershoots.
Big overshoots or undershoots. So the learning rate will scale with the batch size, and usually we will have more node. You have a larger batch size, so the learning rate definitely need to scale accordingly. Okay, so this is comparing the speed up. This measure the speed up, and we compare on different data sets: the Cypher data set, ImageNet, Shakespeare, partition data either IID or non-IID, the baseline is using the fat average. K equal to 5 indicates that we just do the local calculation of the gradient for 5 iterations, sum them up, and then send it out. Okay, so that can have a longer time of communication, but less communication, because we are doing 5 iterations of gradient calculation without any update. We just calculate the gradient. The effectiveness is we are increasing the batch size by 5 times. So that's fat average, increasing the batch size by 5 times. So that's the baseline. And we can do the accumulation of the gradient by 10 iterations without sending them up, just doing the gradient calculation locally, sum them up, and send it out every 10 iterations. So that gives you about 1.5x speed up. And accuracy is well maintained. You can also increase that to 20, you can 2x speed up. The accuracy is also well maintained. But you can also combine that with delayed gradient update. And that can give you 3 to 4x speed up. Well, the accuracy for both IID and non-IID is well maintained across different scenarios. So that gives you another design knob, not only to do fat average, but also you can do the delay. Okay. To verify such idea on a local server, we put up this small rack of Raspberry Pi. Okay, so here we have 8 Raspberry Pis as a real-world benchmark, from 1 node, 2 node, 4 node, all the way to 8 node, across region benchmarks and language benchmarks. So we are comparing the fat average, averaging every 5 step or 10 step, just do local averaging without having to transmit, which is a baseline, very strong baseline. You can get about 3 to 4x speed up with 8 node, but combining that with delayed gradient averaging, you can get 7 or 7.5x speed up with 8 node. Although this is connected by very slow, actually, just standard Ethernet, but it can still scale quite well. All right, so here is a summary of today's lecture. We first talked about mixed hybrid parallelism and how to auto-parallelize, 2D parallelism, 3D parallelism, and then we are faced with 2 challenges. One is bandwidth challenge, the other is the latency challenge. To solve the bandwidth challenge, we have a gradient compression technique using pruning, such as deep gradient compression, or using quantization, such as 1-bit or ternary gradient. To solve with the second problem of latency bottleneck, we talk about this delayed gradient update to allow late days when submitting your homework, when transmitting the gradient, and can still converge quite well. All right, so lab 5 is already due, so we will grade it and return you. Jutta will return the grade by next weekend. Okay, and we also have the whole project's proposal due very soon, so hope you can work on that. If you need any support, feel free to talk to us. We highly encourage you to open source the final projects. For the format of the open source, feel free to check out our labs, GitHub, MIT Hard Lab, search that on GitHub. Pretty much all the projects we did since 2018, since I joined MIT, is open source, which both help you to maintain good quality and also make some help the community to get better. So if you have any questions, feel free to talk to us. All right, that's all for today's lecture. Thank you.